Hi, this is Dr. Green. We're looking at some examples for the week 3 problems. So in this first problem, we're looking at sensitivity and specificity. So these are terms that are used a lot of times with medical testing. But we're using it in the setting of medication compliance. So problem reads that as part of a study, investigators want to assess the accuracy of self-reported medication compliance. Participants are asked whether they took the medications as directed, and then they use laboratory tests to confirm whether or not the medication was present or absent in the blood. So they're going to check up on them. It's like, we're not trusting you, we're doing the blood test here. So here's the information, the data for the problem. So the people that self-reported as non-compliant, they're like, hey, I didn't take my medication. So that's like getting a negative result from a test. And 32 of those people that said, I didn't take my medication, 32 of them really did not take their medication. So medication was absent in their blood. And then 8 people, they did take their medication. So they said, no, I didn't take it, but they really did because it was present in their blood. So that's acting like a positive outcome to the test. And then those that self-reported as compliant, that's a positive result. Hey, I took my medication. So out of those, 24 medication was absent in the blood. Okay, so they either forgot or they're not being truthful. And then for 55 in that group, medication was present, a positive. So they're asking here, what's the sensitivity of that medication compliance? So sensitivity in relation to a disease test is the probability that the person's going to screen positive given that the disease is actually present. So for the disease to be present, that's saying like, oh, well, the medication is present. And the screen positive is saying that they're saying I'm compliant. So this is really a conditional probability. It's the probability that they reported that they were compliant, given that the medication was actually present. So how many people had medication present? Remember, your given your given outcome always determines the denominator in your probability here. So those for which medication was present, that's the 55 plus the 8 here. That's going to be our denominator, second column. And then out of those for which medication was present, how many reported that they were compliant? So out of these guys, the people that reported compliant were the 55. That's our numerator. So 55 out of 55 plus 8. If you key that in the calculator as a decimal, that's 0.8730 or 87.3%. So there was sensitivity of 87.3% in this study. Second question is, what's the specificity? Oh, and our interpretation. So that 87.3%, what does that mean? Well, it means 87.3% of those that actually took the medication, because medication was present in their blood, reported that they were compliant. And then part B is asking, what is the specificity of self-reported medication compliance? So that's saying, what is the true negative rate of this test? So disease is absent, and we're asking, out of people where the disease was absent, how many did the test say were negative for the disease? So that's called a true negative. And your sensitivity is sometimes called a true positive for the test. So in our context here, disease absent is medication absent. So this is a conditional probability. So it's a probability that it's going to be given that medication is absent. And then out of those people, how many screen negative? So that's saying how many said that they were non-compliant. That's our negative. So what's the probability of non-compliant given that medication was absent? So this given condition here, medication's absent, that again determines your denominator of your fraction. So medication was absent in this column, 32 plus 24. And then out of those for which medication was absent, out of this column, how many said they were non-compliant? That's the 32, first row. So 32 out of 32 plus 24. As a decimal, that is 0.5714, or 57.14%. So we would interpret that as saying that 57.14% of those who didn't take the medication, see med was absent in the blood, they reported that they were non-compliant. So that's sensitivity and specificity. In the second exam here, we are looking at the prevalence of type 2 diabetes. It's given us 20% in children 14 to 16 years of age. We took and analyzed 15 children. And then we asked, what's the probability that at least 2 have type 2 diabetes? Well, we have to recognize, first of all, that this is a binomial probability because either they have type 2 diabetes or they don't. Okay? So they either have it or don't. There's only 2 outcomes. So that's telling us it's a binomial experiment. So that means that we're going to use this binomial probability formula to compute. So the binomial probability formula is talking about the probability of successes. In this case, a success for us is having type 2 diabetes. And the probability here of X is our number of successes, and N is the total number in the trial. And that probability is n factorial, remember the exclamation point means factorial, over x factorial, that's the exclamation point, and then n minus x factorial. And then you take your probability of success, which we use little p for that, and then we take that to the x power, and then we take the probability of failure, which is 1 minus p. So if p was 40%, 1 minus p is 60%. And that goes to the n minus x power. So that's the binomial probability formula. So this is probability of x successes out of n. And this n factorial over x factorial, n minus x factorial, that is the number of ways to choose x individuals from n. So, and that's taken into consideration the fact that order does not matter in this example. And this is called combination. So combinations of x from n or selections of x from n. From a total of n. So in our case here, n, our sample size is 15, because we looked at 15 children analyzed. Our probability that we would have success for us is type 2 diabetes. That probability is 20%, so p here is 0.20. And then x is going to be our number of successes, or our number of diabetics. So we're asking here, what is the probability of at least 2 having diabetes? So at least is it greater than or equal? So we want to know what's the probability that x is greater than or equal to 2. Well, it's easier to look at the opposite probability and subtract from 1. So look at the probability that the number of diabetics is less than 2, subtract that from 1, which is 100%. So you do this a lot of times with binomial probabilities. Well, how many ways are there for x to be less than 2? It's got to be a positive number, so x could either be 0 or it could be 1. So you figure those two probabilities from this formula, and then you add them together. And you subtract from 1. So let's go ahead and figure those probabilities. So probability that x is equal to 0. Okay, so n is 15, so this is going to be 15 factorial up on the top. And then down on the bottom we do x factorial. Well, our x is 0, so that's going to be 0 factorial. And then here, 15 minus 0 is going to be 15 factorial. So remember, factorial means 15 times 14 times 13 times 12, all the way down to 1. That's what that means. And then our probability of success is 0.2, and that gets an exponent x. For us, in this case, that's 0. And then 1 minus 0.2, which is 0.8. So that's the probability of failure. That gets an exponent of 15 minus 0, or 15. So if you key this into your calculator, you will get 0.0351. Now, here you can simplify this and get a 0.8, and then 15 minus 0 is just 15. This part is the one that takes a little bit of work on your calculator. And I would just use an online combinations calculator to figure that. So I did a web search here for combinations calculator, and this was the first site that came up, Calculator Soup. And they sometimes use this notation for the combinations instead of the factorial notation. So our total here was 15, and we were doing 0 successes, so r or x is 0, and you just press calculate, and here it tells you the answer is 1. Okay, so, and that makes sense here because look, 15 factorial divided by 15 factorial, anything divided by itself is 1. Okay, and then 2 to the 0 power is 1, and then 0.8 to the 15 power, that's the 0.0351. So then that gives us this number here. So this is now 1 minus probability of 0 is 0.0351. And now we just need to put in the probability of 1 success, and we got it. So if x equals 1, this 0 here changes to a 1. And then down here, instead of 15 minus 0, it's 15 minus 1, 14 factorial. And this 0 turns to a 1. And then this 0 turns into a 1. So again, this number out in front, if you don't have combinations on your calculator, just go to the combinations calculator and Calculator Soup. So I'm going to change that to a 1, press calculate, and 15 now is that answer. So this is 15. So it'd be 15 times 0.2 to the first power times 0.8 to the 14th power. So if you key that in, you'll get 0.1391. Oh, I'm sorry, 1319. And so if you add those guys together and subtract from 1, you will get 0.8330. So there's an 83.3% chance that we would have at least two children that would have diabetes. So I included another calculator in here that you could double check your work with. Part B asks us, what is the probability that exactly 5 would have type 2 diabetes? So that's saying, what's the probability that x equals 5? So again, that's this same formula that we used up here. Everything's the same except that 1 is now 5. Here, 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 and here. So 15, choose 5. So go back to our combinations calculator, 5, and calculate. So that number out in front now is 3003. So this is 3003. And then the rest of this you can do okay on your calculator. That's just powers. So if you do the calculator work on that one, you will get 0.1032. So 10.32% chance we'd have exactly 5 out of the 15 that would have diabetes. And then they ask how many would be expected to meet the criterion for type 2 diabetes with a probability of 20% for any random person. And expected is asking what's the mean. Remember, we use mu for the mean. For a binomial distribution, the mean is the number in the sample times the probability of success. So that's our 15 times our 0.2 probability that any random adolescent has diabetes is 0.2, which gives us 3.0. So you'd expect on average that 3 out of 15 would have diabetes. And then in the last example problem here, next to last, we're looking at a researcher who wants to know the probability that an individual's body temperature would measure above 102.4. This researcher found the z-score corresponding to a 102.4 temperature is 2.14. And we want to know what's the probability that the random individual's body temperature would measure above 102.4. Okay, so what's going on here is that we know a z-score. Okay, so it says the z-score corresponding to 102.4 is 2.14, and so that tells us z is equal to 2.14. And if you are using z-scores here, that means that the data has to be normally distributed. So the z-score that corresponds to 2.14, to 102.4 is the 2.14. So they're asking us, what's the probability here that an individual body temperature would be above 102.4? So the individual body temperatures, those are x values. So we're asking, what's the probability that x is greater than 102.4? Well, the z-score being 2.14 is saying, well, that probability corresponds to z-scores, normal distribution, being greater than 2.14. And then this is a table problem in the back of the book using the standard normal table. So remember, the table in the back of the book only gives less than probabilities, so we have to use the complement probability and subtract from 1. So this is going to be 1, or 100%, minus the opposite probability, the probability that z is less than 2.14. We could do less than equal, they're the same. So this we can look up in the table. So now we go to our standard normal table. So this is table 1 in the back of the book. And again, see, these numbers represent z is less than a specific z value. So like z less than negative 1.96. We want 2.14. So let's see, this is the negative side of the table. Go to the next page. So the 04 column is here. And then the 2.0 is down at the 04 column is here. And then the 2.0 row is down here. So 2.00, 01, 02, 03, 04 right there. 9793. So this is 1 minus 0.9793. And if we subtract those on the calculator, we get 0.0162. So that's a table problem. And then our last problem that we're looking at here is saying, assume that you've got a random sample of body temperature measurements from 28 individuals. So not just one measurement, but 28 different measurements from a population. And we know the mean of the population is 98.6 degrees. That's your normal body temperature on average. Some people lower, some people higher. And then the standard deviation of the sample is 1.54 degrees. Calculate the probability that the mean body temperature for the whole sample will be above 100. So that's saying the mean of those 28 people that we took measurements from. So let's list what we know here. So we took measurements from 28 individuals. That's our sample size, so n equals 28. They said the mean of the population is 98.6, so that's mu is 98.6. And the standard deviation here is 1.54. So that's your S, that's sample standard deviation, is 1.54. And what we need to know is information about the mean of the 28, not an individual, but the mean of all of them. So remember, when you take a collection of measurements and you find the mean of those, you're talking about the sampling distribution. So this is not the mean of the x values, but it's the mean of a group of sample means. So we use that by putting a little x bar down here. So it's the mean of x bar values. And remember that the x bar distribution has the same mean as the original distribution, 98.6. So if you took a whole bunch of samples of size 28 and you figured the mean temperature of those samples, you should still get 98.6, because that's the mean for the population. And then the standard deviation for all those samples of size 28 is going to be the standard deviation of our sample, the 1.54, standard deviation of one sample, divided by square root of n. So square root of the sample size, that's the root 28. And so if you compute this on your calculator to 3 decimal places, you'll get 0.291. So now we can figure the z-score of this 100 degrees, that the mean of that sample of 28 individuals would be greater than 100 degrees. We can find the z-score that goes with that. Then we can use the normal table. So z-scores are the value minus the mean over standard deviation. So you're used to seeing this, z equals individual value minus mean over standard deviation. Well, we're doing that, except we're not looking at x values, we're looking at x bar values. We're looking at means of samples, not individual measurements. So that's why the extra x bar is here. So our x bar value, we're looking at the mean of the sample being above 100. So our x bar value is 100. Our mean, 98.6. And then our standard deviation is the 0.291. So if you compute that to 2 decimal places, remember you always do z-scores to 2 decimal places, you'll get 3.09. So to say that the mean of, this should be not 100, this should be 99.5. Miscopied. So we want to know what's the probability a mean of a sample would be above 99.5 degrees. So we write that like this. What's the probability that an x bar value, a mean of a sample, would be above 99.5? So it's the 99.5 minus the 98.6 over 0.291. That gives our 3.09. So this is the same as saying the probability that a z-score would be above 3.09. Well, remember the table only gives us less than probabilities, so we have to change this to 1 minus the opposite probability. So probability z is less than 3.09. And then this we can look up in the table. So we go back to our table, standard normal table in the back. We go down to the 3.0 row down here on the bottom, and it's this very last column is the 0.09 column, 0.9990. So this is 0.9990. So 1 minus 0.9990, which is 0.001. So there's our probability. So probability that the mean of that whole group is above 99.5 is only 0.001, 0.1%. So it's easy for one person to get above 99.5 degrees, but not a whole sample of 28. So that's what's going on in this problem. So hopefully that will help you out with the homework exercises from week 3.